Good morning, guys. So, guys, we're just moving along with our trigonometry units. Almost finished it. So this topic, number 6.3 in the trig identities unit, and the topic is called proving identities. So we covered a lot of the stuff in section 6.1, but now we're applying some of the identities that we learned in 6.2, the double angle and the sum and difference identities, to some more complex identities that we can prove those with as well. So first example, we have to prove the following identities. And guys, the way we do these proofs again is we call a two-column proof. So for two-column proof, I'm just going to draw a line down the middle. And we need to make the left side of this equation look the same as the right side of the equation. Okay. So general rule, guys, we're trying to make everything in terms of sine and cosine. So we know that tan x is the same thing as sine over cos. And we're multiplying times cosine x. And that cosecant x is the same thing as 1 over sine. Okay, so a bit of cancellation here. The cosines are going to cancel. And then we're left with this like sine x over 1. So we're left with like sine x over 1 divided by 1 over sine x. So it means we can multiply by the reciprocal. And that gives us sine squared x. Okay. Now on the right hand side, we have 1 minus cosine squared x. So we're going to be looking at our main Pythagorean identity. And all I'm going to do is subtract cosine squared from both sides. That means sine squared equals 1 minus cosine squared. So 1 minus cosine squared is sine squared. And we have then proved the left side equals the right side. Now, a few things. We have some non-permissible values to account for. We have a cos x in the bottom, and we have a sine x in the bottom. So that means sine x can not equal 0, and cosine x cannot equal 0. And that happens on the axes points, which are these four guys here. So we know that x cannot equal pi over 2n, where n is an integer. Okay, so we've shown that the left side equals the right side, and we're going to kind of our concluding statement for these proofs, guys, is either drawing the tombstone, which says we've proven it, or to write the letters QED. And again, guys, QED means which was to be shown, or you could just put your little box and fill that in as well. And this is our concluding statement that we have proven our identity. Okay, so this is how this one works. We need to prove that tan x equals sine 2x over cos 2x plus 1. Okay, same thing. Let's go ahead and do our two-column proof here. So we have tan is the same thing as sine over cosine. We know that sine 2x, this identity here, is 2 sine a cos a. So we're going to make this replacement here and make it 2 sine x cos x. And now we have a bit of work to kind of be able to work on our bottom, our denominator of this side over here. So we want to be able to get a cos 2x plus 1. So hopefully, guys, you can see that we're going to use this identity over here, because we want to get a cos 2x plus 1. So the way we can do that is, since we have a minus 1 on the right-hand side of this identity, if we add plus 1 to both sides, we get cos 2 alpha plus 1 equals 2 cos squared. So this is going to replace the denominator of the right-hand side of our fraction here. So we get 2 cosine squared x, and then the 2's cancel out. The cosines cancel out, and we're left with sine x over cos x. Okay, and so we have the left side equals the right side, which was to be shown. And now let's just consider our non-permissible values here. We have a cosine in the bottom of these fractions over here, so that means that cos x cannot equal 0, which happens at the top and the bottom of our circle over there. So that means x cannot equal pi over 2 plus pi n. And so again, this is going to be kind of the top. If you go plus pi, you hit the bottom, plus pi like this. And it's going to count for all of our non-permissible values here. Okay, so we've proven the identity, we've included our non-permissible values, and we have made a concluding statement over here to say that we're finished this question. We're finished this example over here. All right, so moving on, guys, we're just going to keep on doing more of the same here. We have cosecant 2x equals cosecant x over 2 cos x. So cosecant 2x is the same thing as 1 over sine of 2x. Okay, so the cosecant is the reciprocal of sine, and now we're going to apply our sine 2 alpha formula. So it's going to be 1 over 2 sine x cos x. On our next one, we have on the right hand side, we have cosecant in the numerator. So it's the same thing as 1 over sine x. So what I'm going to do with the denominator, I'm just going to make this guy 2 cos x over 1. I don't want to make it so I'm dividing a fraction by a fraction like this. So now I'm going to multiply by the reciprocal. So it's 1 over sine x times 1 over 2 cos x, which is 1 over 2 sine x cos x. So our left side equals our right side. Let's just state our non-permissible values. We have sine and cosines in the denominator. That means sine x cannot equal 0 and cosine x cannot equal 0, which happens on the axes points. Guys, it tends to be that these are often the non-permissible values for these type of questions over here. That means x cannot equal pi over 2n, where n is an integer, and here are our non-permissible values. So we have completed our proof over here. Okay, let's keep on going. Okay, so we have sine 2x over cos x plus cos 2x equals cos 2x over sine x equals cosecant x. Okay, trickier question for sure over here. Where I'm going to start for this question is I'm going to add both the fractions together. Okay, now to do that we need to get a common denominator. Okay, so for this one we have a cos x in the bottom, but we need a sine x in the bottom, so I'm going to multiply this guy times sine x over sine x. For the second fraction we want to have a cos x in the bottom, so I'm going to multiply the top and the bottom by cosine x. So what we get is we get sine x sine of 2x plus cos 2x times cos x over sine x cos x. And on the right hand side we have cosecant x, which is 1 over sine x. Okay, now this is getting quite long on the left hand side over here, but we're going to start applying some of our identities that we have here. Okay, so what we have a sine 2x here, so we'll apply our sine 2x formula. This is going to be sine x times 2 sine x cos x. Now the one I'm going to do for this one over here is, we don't use this one too often yet in these notes, but we're going to use this identity here. So we're going to use our cos squared minus sine squared. So for this one we have cos squared minus sine squared times cosine x all over sine x cos x. So this gives us, I'm just going to multiply this through, so we have sine x times sine x. This is going to be 2 sine squared x, plus, now I'm going to multiply this through like this, and we have cos cubed x minus cos x sine squared x all over sine x cos x. Guys, I made a mistake. There should be no plus here. So this one over here was this minus this times this. So there's only one term over here. So this should be 2 sine cubed x. No, sorry, 2 sine squared x times cos x, like this. Okay, so looking at this over here, we have 2 sine squared cos x minus, and now with sine squared cos x as well. So hopefully what we see is that these guys are actually like terms. So I can just subtract them, because this is sine squared cos x and this is sine squared cos x. So this is going to be the same thing as 1 sine squared cos x over sine x guys. I made a few mistakes over here. I need to go and make a few mistakes. I need to go correct this. Guys, I'm going to erase from here. Sorry guys, my mistake over here. I couldn't sleep this morning, so it's currently 4 o'clock in the morning right now, and I decided to go in and just wake up and make one of these videos, and I'm clearly not awake yet. Okay, let me just go back and fix this example here. Multiplying this over here, we have 2 sine squared x cos x, and when I multiply this through, this is going to end up being a cos cubed x minus sine squared x cos x. There we go. Okay, so I think this is going to be better for us now. And over sine x cos x. The step we're going to do next is we have a common factor of cos x in all 3 of these terms over here. Okay, so we have cos x, and we're left with 2 sine squared x plus cos squared x minus sine squared x all over sine x cos x, and this cos will cancel out with this cos over here. And I got to kind of finish this side over here, guys, because I'm running out of room. Continuing to simplify the numerator, we have 2 sine squared minus sine squared is going to leave us with sine squared plus cos squared over 1, and over sine x. And we know, guys, from our Pythagorean identity that sine squared x plus cos squared x equals 1. So I'm going to replace this 1 over here, and this gives us 1 over sine x. There we go. Okay, so now, guys, this is still the left side I was working over here, but the left side equals the right side. So I'm going to go right side equals left side. And we have our non-permissible values to account for. We have sine and cos are both in the bottom. So that is going to be our axes points again. Sine and cos happen at these equals 0 happen at those 4 points. So we have x cannot equal pi over 2n, where n is an integer. Now we're going to write our tombstone sign, which means that we've completed our proof and we are finished. Okay, so this is an example. We saw examples similar to this in section 6.2 as well, but we're going to have to use a sum identity for sine. So we have 3 pi over 2 plus x. This is the same thing as one of our sine a plus b identities over here. Okay, so in this case, a is 3 pi over 2 and b is x. So applying this identity to the left-hand side, we get sine 3 pi over 2 cos x plus cos of 3 pi over 2 sine x. And we're trying to get this to equal to negative cosine x over here. So just 3 pi over 2 is a value on our unit circle. So here's 3 pi over 2. And the coordinates here are 0, negative 1. So when I apply in sine 3 pi over 2, this is going to be a negative 1 times cosine x. Cos 3 pi over 2 is 0, so it's plus 0 times sine x. So this part goes to 0, and we're left with negative cos x equals negative cos x. So in this case, we have no non-permissible values because there are no variables in the denominator as well. So we're finished this one, and we can go left side equals the right side. And I'm just going to put QED. This again means the same thing as the tombstone, guys, but we mean that we have shown the left side equals the right side, which was to be shown, and we're finished this proof here. Okay, moving forward, we have sine x minus cos x plus sine x plus cos x squared equals 2. So, guys, I'm just going to put this like equals 2 over here, just so I have a bit more room on this one over here. So when we do this, we need to actually expand this term and this term over here. So this means we have sine x minus cos x times sine x minus cos x plus sine x plus cos x times sine x plus cos x. Now we need to be able to distribute, use our distributive property for each of these two multiplications. So for the first one, we get sine squared this is going to be minus sine cos as well, so it's going to be minus 2 sine x cos x plus cos squared. For this one, similarly, sine times sine is going to be sine squared. We have sine cos is plus 2 sine x cos x. Cos times cos is cosine squared. Okay, so big long expression over here, but we're going to have a negative 2 sine x cos x and a positive 2 sine x cos x, so those two terms are going to cancel each other out. Now, what we're left with is we have a sine squared plus cos squared, which is equal to 1, and we have sine squared plus cos squared, which is 1 as well. So there we go, 2 equals 2. Okay, we have no non-permissible values to account for in this example either, because there's no variables in the denominator at all. So we have our left side equals the right side, and we're finished this proof over here. Okay, definitely a more challenging one over here. We have cotangent minus cosecant equals cos2x minus cos x over sine 2x plus sine x. Okay, so starting with cotangent x, we know that cotangent is cos x over sine x. Cosecant is 1 over sine x. So I'm just going to do a bit more work on the left-hand side over here. We already have a common denominator of sine x, so that means I can subtract my numerators, and we get cos minus 1 over sine. So we need to work on the right-hand side now and get that to equal this guy over here. So the trick for this question is we're going to have to be able to do some factoring of our numerator and denominator to be able to make some cancellation happen here. I'm going to start on the bottom. We have our sine 2x, so I'm going to be using this identity here. So we have 2 sine x cos x plus sine x over there. Now, the one I'm going to use for this one is I'm going to use my middle cos2 alpha identity, and I'll show you why in a second. Well, what I want is I want to get an expression that only has cosines in it in the numerator. Okay, so this one over here, it gives me a 2 cos squared minus 1, and I already have a minus cos x here. So again, we're making this replacement here. So this becomes 2 cos squared minus 1. I'm just going to rewrite this guy as 2 cos squared minus cos x minus 1. And on the bottom, hopefully we don't recognize that there's a common factor of sine x. Now, if you look on the left-hand side, we know that we want to have a sine x in the bottom. So hopefully we recognize that we want this 2 cos minus 1 to end up canceling out with something in the numerator. Okay. Now in the numerator here, we have this is like a quadratic trig expression over here. So this is 2 cos squared minus cos minus 1. So just off to the side here, like if I have this expression over here, so all I've done is I've replaced cos x with a. This is a little bit easier to factor, I think. So if I have to factor this guy, it goes 2a minus 1, and then a plus 1, like this. No, I messed that up. It's a plus there, and that's a minus there, and I also made a mistake. This should have been a plus 1 right over here, not a minus 1. So there we go. So just factoring it this way, we can just kind of apply this factoring rules to my numerator here. So this is going to become 2 cos x plus 1 times cos x minus 1 all over sine x 2 cos x plus 1. And now these guys cancel out, and we're left with cos minus 1 over sine x. Okay. Now this last example that we're doing here is going to be a case where we actually have some different non-permissible values. Well, this guy's the same. We have a sine x in the denominator, so we know that sine x cannot equal 0. But we also have this guy in the denominator as well. So that means that 2 cos x plus 1 cannot equal 0. That means that cos x, I'm going to subtract 1 divided by 2, cannot equal negative 1/2. Okay. Our non-permissible values here, sine equals 0 here and here. So I'm going to say that x cannot equal, I'm going to call this guy pi n. So this goes like pi, 2 pi, 3 pi, 4 pi, 5 pi, and so forth like this. Now my cos x cannot equal negative 1/2 happens here and here. This is at 2 pi over 3, and this is at 4 pi over 3. So I'm going to say that x cannot equal, like, because the only pattern over here is I have to do this one individually and then this one individually over here as well. So there's going to be 2 pi over 3 plus 2 pi n, where n is an integer. And the last one, we have x cannot equal 4 pi over 3 plus 2 pi n, where n is an integer as well. Okay, so we've listed our non-permissible values for this case. We've shown our left side equals our right side, left side equals right side, and which was to be shown. So we've completed this proof, and this was definitely probably the more difficult one that we've done so far. Okay, so guys, these questions definitely do take a lot of practice. So make sure you're keeping up with your textbook questions for practice for the stuff we're here, guys. And as always, guys, please come and let me know if you have any more questions of this. Okay, I will see you in the next video.